Hello, my name is Nicholas Harmon. I'm from the University of Evansville, and my talk today is entitled Magnetoresistance Measurements as an Alternative to Magnetic Resonance Methods for Studying Paramagnetic Defects. This was supposed to be in the session S19, New Opportunities in Spin Sensing, Manipulation, and Resonance Without Time-Varying Magnetic Fields. So obviously there will not be time for questions at the end of this talk, so I encourage you to please email me any comments or questions you might have to my email address below there. Okay, so first I'd like to thank the organizers for inviting me to speak at this year's APS. I'd then like to acknowledge my collaborators on this work. This is Michael Flatte and Stephen McMillan, who are at the University of Iowa. And then, they work on the theory side with me, and then Pat Lenahan and his group at Penn State work on work on the experimental side. And then this work was funded by the DTRA. Okay, so first I'm going to introduce transport through defects at ferromagnetic junctions or non-magnetic junctions. And this will illustrate the physical effect that underlies my talk today. And then I will speak on spin-dependent recombination and electrically detected magnetic resonance, or EDMR, and look at a specific case of phosphorus-doped silicon. And then I will talk about near zero field magnetoresistance. Okay, so you're probably pretty familiar with magnetic resonance techniques as well, NMR, EPR, then ODMR and EDMR are optically detected and electrically detected magnetic resonance. And these are very useful techniques. Obviously, NMR or MRI is used often in the medical fields. Then EPR can be used to detect properties of defects. That's primarily our interest in this talk today, is looking at defect characteristics using these type of methods. And all these techniques, of course, rely on some alternating field, radio frequency or microwave frequency magnetic fields. So this is actually a limitation in that one can't use these techniques to probe the defects within 3D integrated circuits. Okay, and this is due to the highly conductive elements that shroud the layer you might want to look at. Okay, so these electromagnetic waves will be shielded. Okay, so there's some limitations there. And the idea behind this talk is to look at a new technique that doesn't rely on an alternating field. Okay, and that's this near zero field magnetoresistance, which I will introduce. Okay, so this near zero field magnetoresistance is an entirely new effect in terms of the physics of it. It was first actually, the underlying physics was first looked at in chemistry, in spin chemistry, looking at field-dependent chemical reactions. And then more recently, it was looked at in organics, this so-called organic magnetoresistance, or OMAR effect, where large room temperature responses in transport or recombination were observed. So here's magnetoconductance of this polymer, and then here's magnetoresistance in the small molecule AlQ3. So to understand how this effect works, I thought it'd be good to go through an example which is peripherally related to my main point of this talk today, and that is looking at transport through a defect which is situated at a ferromagnet and non-magnetic junction. Okay. All right, so some of you may be familiar with a 3-terminal device for spin injection, which is somewhat controversial, I should say. Like here you have a ferromagnet, which is serving as an injector and detector, spin injector and spin detector, into this magenta semiconductor down here. And the Hanley effect is used to measure, or used to determine whether there's spin injection or not. And it turns out that in many cases the Hanley effect is not really, what is being thought of as the Hanley effect is not the Hanley effect, but instead is a magnetoresistance effect due to a defect situated in this layer here between the two electrodes. So let's go through how that defect can modify the current when you apply a magnetic field, which will mimic this Hanley effect. All right, so here is the ferromagnet, here's the insulating barrier, and here's the non-magnet. And let's walk through how a charge might go from the left to the right. Okay, so key here is that we have a trap, paramagnetic trap in the middle here, and you have this excited state, which is in this bias window. So if the left electron hops into the trap, it's now doubly occupied. Well, I'm showing here they're both parallel spins, and this, of course, is not going to be allowed by Paul exclusion principle, so that can't happen, and you have a bottleneck here. If the spin is down, then the trap spin is initially down. Well, that's okay. We don't have the bottleneck anymore, and you can hop to the right. Okay, so here's there is no bottleneck, and you will have a current. Okay, so okay, this is just showing the other way. Either spin can hop to the right. Okay, and the other spin goes back down. Okay, now another way to get rid of the bottleneck, or a way to get rid of the bottleneck, is by applying a magnetic field. Okay, this will cause transitions within the lower energy state of the defect, and the relative orientation of the trap spin and the ferromagnet spin will change and become anti-parallel, and that's, of course, is the case where we can hop to the right. So we get current. So by turning on this field, we can release the bottleneck. Okay, so we see here is a form of magnetoresistance. This can be modeled quite easily with a simple rate equation model for this upper state. This was done in this paper down here. And you have an expression then for the current through, which depends on this magnetic field, and of course its orientation is important as well. And this effect can explain these spin injection measurements, many of them. Here are some results in STO, LAO, and cobalt junction. Here's the experiment, here's the theory. Blue matches with blue and black with black here. This is voltage and current, so they're opposite. And there's very good agreement between the two. Notably, there's a ratio of amplitudes, so this would be delta I perp, delta I parallel. Perp refers to the orientation of the magnetic field with the magnetization of the ferromagnet, and here's parallel for the parallel orientation of the field in the ferromagnet. And we see this ratio of 2, and this is to be a signature of this defect-mediated conduction. Okay, so the systems I'm going to be talking about and that we're looking at experimentally are not ferromagnetic. So let's now look at a non-magnetic situation and see if we can also get a magnetoresistance. And it turns out we can, as long as we have a second state or second defect within this insulator. So here's our defect we had before, and now we have a defect here which goes, it's either going to be singly occupied or unoccupied, where this goes between single and double occupation. Okay, so let's see what happens when we step through this process. That's okay, spin independent step. And of course now to continue on, the orientation of the spins will matter. Okay, so what we have then, we have two spins that are exclusive to one another. Okay, so in some sense they're stuck here, and they can't get out of the situation. So that's fine. It can go to the right, just as we talked about. Now, of course, here we're going to have a problem, right? Okay, so we see very similar feature as we did in the ferromagnetic case. We just need to incorporate this localized state here, which acts like kind of like a spin polarizer, because once the electron comes here, it's now completely polarized. Okay, so it's kind of like a ferromagnet there. All right, so magnetic field now, before we alleviated the blockade by applying a magnetic field, so if we do that here, it actually doesn't help if we have a uniform magnetic field, because they're both going to have the same precession. A uniform magnetic field does not change, your relative orientation. So, okay, but we can add in the oscillating field, B1. Okay, and of course now we have magnetic resonance. Essentially, this is what EDMR is. It's the modulation of the transport with this B1 field. Okay, and here we go. We now cause a spin transition at one of those sites. Okay, and this then alleviates the bottleneck again. Okay, so now, sorry, went backwards there. All right, so now let's look at this effect of near zero field magnetoresistance, which does not have this alternating field at all. So let's say we're in this state, right? We're blocked, okay? However, we can still alleviate this bottleneck through spin transitions, and these occur even at zero field. Okay, so no resonance field. And let's say they have two different G factors. And we have a magnetic field out of the plane here. Two different G factors. Let me go through that again. Two different G factors, so they'll precess at different rates, and the relative orientation will be changing. And at some other time, we'll see that they, in fact, are now in an anti-parallel state, which allows for the blockade to be broken. Okay? So that essentially is the near zero field effect, is that you have these spin transitions near zero field due to the different environments of the two sites. Okay, so I've looked at the transport model. Now the experiments we're looking at today are primarily going to be in the recombination regime, not with transport. And what I've said really carries over to recombination with our problem. It'll be a spin-dependent recombination. So here is an example, a little pictorial of that. So here's our conduction band, valence band, and we have a defect in the middle here. And then we have some other maybe impurity, some sort of low-lying shallow donor state, let's say. And a free electron might be trapped by that donor, and then it can either dissociate with rate KD, or it could be captured by the deep defect at rate Ks. Okay, so you have these two different processes that can occur. The pink with the little arrows in, that's mimicking or modeling the hyperfine fields that might might be at these different sites. Okay, so then let's say it gets captured, so now we're over here, we have a doubly occupied state. And of course, this capture process, that's what's spin dependent, right? Because again, we're going to have Pauli exclusion principle, so we're going to form a triplet here, or sorry, singlet here. And then at this point, a hole, free hole, will recombine with the defect, okay, and then you get back to here, which is the neutral state. Okay. All right, so how do we model this spin-dependent recombination? And the model actually is very similar in that that would be used for transport, but I'm going to focus on recombination here. So we use a stochastic Liouville equation. This can be used for EDMR and the near zero field effect. And we'll walk through some of these terms here. So this right here is your normal Liouville equation, right? There's your coherent evolution in the various interactions you might have. And then over here are sinking terms, and this is basically this is the term that takes out singlet parts of the density matrix. So this density matrix is composed of these two electron spins, let's say, and then whatever nuclear spins you might have present. Okay, so this takes out singlet electron spins at these rates, right? Ks, Kd, and then Kt plus Kd is the rate at which triplets are leaving. Okay, now triplets aren't really being captured in the model I showed you earlier, but triplets can dissociate, so they can leave through dissociation channel. So PS and PT are projection operators, and this is the generation of these spin pairs. We're looking at experimentally what's being measured are recombination currents, so we can look at an expression for recombination current, and what's going to be spin dependent here is our capture. This sigma s is the capture of the deep defect with one of these shallow donor spins or free spin and whatnot. So this sigma s needs to have some spin dependence, so we can relate that to the density matrix in the following way. The capture cross section would scale as the square root of the singlet probability for the spin pair. Okay, so the interactions are going to go into our stochastic Liouville equation. We're going to have obviously Zeeman interactions with the two spins, S1 and S2, the two electron spins, and then we might have nuclear Zeeman as well if we have nuclear spins and are caring about hyperfine interactions. And then we have the hyperfine interaction here with, in general, of course, would be with both spins, but here I'm only showing with one spin. And then if we're using EDMR, we'll have the alternating field, okay, which looks like this. And when we are doing EDMR, we're using rotating wave approximation, which modifies the Hamiltonian in this manner, which eliminates the time dependence, which makes it a much easier problem, of course. And then in EDMR, we're going to take the secular approximation, which means we're looking at high field resonance. Okay, and that simplifies the hyperfine Hamiltonian. Okay, so let's talk first about EDMR a little bit. All right, so here's a schematic of the process again. We have a spin coming into this shallow donor state, S2, with a rate G, and then it could dissociate, which means get out of there and go back to the conduction band, or it could recombine or be captured by the defect at a rate Ks, and the defect has a nuclear spin, let's say. Okay, so let's think about the resonances that appear with this process going on. So here is the energy eigenvalues of the Hamiltonian I showed you earlier. And let's look at the possible transitions we can have. Okay, so here I have these kets. Okay, let's think about these kets. The first spin is the defect spin. The second spin arrow is the free spin, and then the third thick arrow is the nuclear spin. Okay, let's correlate this with the energy eigenvalues and look for the possible resonances. Okay, so let's look at the orange one here. The orange line is corresponding to this state here, and then the black line is corresponding to the all-up state. Okay, and then we see we have an intersection here, so it's possible we would have a resonance there. Okay, so this resonance is a flip of the second state, so that would be S2 state. That's being flipped by the RF field. Okay, that's how we go from there to there, and we can determine this analytically. It's this value for the resonant field right here, and of course this is not modified by the hyperfine field. Right, there's no hyperfine interaction in that resonance, and that's because the S2 spin doesn't have a hyperfine interaction at it. Okay. Now contrast that with the blue line and black line intersection. Okay, so here's our blue line that corresponds to this state, and then the black line again is the all parallel state. Now here we do have a modification with the hyperfine interaction. Okay, so this occurs at minus A over 2. And then we'll have another resonance over here at plus A over 2 relative to the center peak. Okay, so let's think again about what's happening when we have these resonances, right? So in the first case, we have all up, and there's no recombination between the free spin and the defect spin because they're parallel. We flip the defect spin. We flip the free spin with the alternating field. Okay, so now we have an anti-parallel configuration and we have recombination. Okay, so that's why we're getting recombination there. Over here, no recombination for the left state, and on the right state we flip the field, and we have we flip the other field, right? We flip the defect spin. Okay, and that now allows for recombination. Of course, the field at the defect spin is not just the magnetic field, but also it has this hyperfine field, so that's why you have this hyperfine splitting. So we have these analytic answers here, which are pretty simple to find. And there's actually a really nice example of EDMR in a pretty well-known system of phosphorus doped silicon, where we can study it in detail and use it. Really helpful when trying to really easy to model. So here's more or less the schematic I showed you earlier. We have conduction valence band. We have now a phosphorus state, which is a shallow donor, always has a nuclear spin of 1/2. And then we have this lower state, which is the PB state, PB0 state. So the PB defect is a spin 1/2 defect. It forms at the silicon dioxide surface interface, and it's essentially a dangling bond there. So what happens here now is that we have a spin being captured into the phosphorus, and then that spin, if it's in the singlet configuration, can drop down into the PB0 defect, which then is captured by a hole. So this is the recombination process. Okay, so here's an experiment from this source here. This is looking at the EDMR, and we see we have our splittings of the 4.2 millitesla of the defect spin, and then here is the PB0 spin right here in the middle. And the reason why it's not directly in the middle is because it has a different G factor, so it gets a shift. And there's no splitting there because at 0th order approximation has no hyperfine field. It's not completely true, as I'll discuss shortly. We'll look at that will play a role in the new zero field effect. Okay, then here is the calculation using the stochastic Liouville equations I introduced for the system, and we can produce those peaks fairly well, at least their positions. I mean, this does not include decoherence, actually, so that will cause some broadening. And then also we do pick up other resonances, higher order resonances that are not resolved in the experiment. Okay, so here's an example down here. Okay, so now let's think about the Hamiltonian for the near zero field magnetoresistance effect. So here we have to really consider the hyperfine interaction and how we want to model it. So we could include quantum nuclear spins. Okay, so we have this hyperfine interaction, and we could have any number of nuclear spins. Of course, the larger the number of nuclear spins, the larger the operators we need to use. So there's some computational issues you run into. And an alternative is a semi-classical or mean field approximation for the nuclear fields. And this takes into account that different defects will experience different numbers of nuclear spins near it. For instance, in silicon, right? Silicon-28 does not have a nuclear magnetic moment, but silicon-29 does. Silicon-29 occurs a little bit less than 5% of the time. So you have some statistical distribution of numbers of silicon-29s around these defects. So if you use a semi-classical approximation, essentially you are getting rid of the nuclear spin operators, and you're substituting in this B sub n1, B sub n2 for nuclear fields at the two spin sites, and those nuclear fields might be drawn from a normal distribution. Okay, so for the quantum nuclear spin 1/2 case, we can solve that exactly. Solve for the eigenstates and eigenenergies exactly. You get this right here. Of course, we don't have a resonant field, so we don't have the same spin selection rules, right? Our spin selection rule is not delta m equals 1, it's delta m equals 0. So as long as we are obeying the spin selection rule, we are allowed transitions between these various 8 eigenstates. Okay. So while the total delta m is 0, the delta m for this total electron spin does not need to be 0, and neither does the total delta m for the nuclear spin need to be 0. Of course, the sum needs to be 0. So we have a shuttling between electron and nuclear spins due to the hyperfine interaction. So this state here would be a bottleneck state because they're both parallel. Hyperfine interaction will reduce transitions, which will cause anti-parallel and reduce the bottleneck. So this is the essence of the near-zero field effect. All right, so here's a calculation of the quantum model, spin 1/2, also including EDMR, because that can be easily incorporated as well into the theory. These are different values for these parameters Ks and Kd, the capture or dissociation rates. And you can see they depend strongly on them. So here's what I would call a large Ks, Kd, and reducing these values. And the features change pretty dramatically. Here you have relatively broad features, and then they narrow considerably. Here you have no EDMR showing up. It's very small. Here, as you decrease the rates, you start increasing the EDMR. And we see our 3 peaks for the EDMR, as expected. What's interesting, though, is this feature around a very small field, okay? And this field actually becomes very large as you increase or decrease these rates, the Kd and Ks rates. It dominates the line shape. Okay, so the way to understand this, we call this a small field effect. So here's the integrated data. Here's the derivative data. Everything I've been plotting have been the derivatives of the rho sub s. Okay, so here's derivative of rho sub s, and the reason for that is it's what they're measuring experimentally is actually going to be the derivative of rho sub s, and also shows features more clearly sometimes. But here's the integrated value of of rho sub s, and here's the derivative. So how do we understand the small field effect? Well, let's look at the integrated value. So we can think about this basically following the line of following current. So think about this as current. So in zero field, right here, j squared and jz are conserved. Okay, total spin is conserved. In small field, only jz is conserved. Okay, so remember that we're breaking bottlenecks because we have these spin transitions, and the spin transitions, of course, must obey angular momentum conservation. So in zero field, we have we have more strict rules on the transitions, don't we? Because we have two conservations to obey, whereas in small field we only have one. So we have more possible transitions, and this allows the bottlenecks to break easier and for the increase in current that we see. Okay, and then as we get to even higher fields, larger than the hyperfine fields, well, now you have Zeeman splitting, and this will reduce transitions further and cause the downward trend. Okay, so large responses in transport or recombination have been seen in a lot of systems, and really Pat Lenahan has done a lot of great work in a various number of systems looking at this. So I point to you for this paper right here. I would have you look at. Has a lot of examples, and the previous presentation by Pat, just before mine, was entitled this right here. So looking at much more of the experiment side of things than what I'm showing you today. So check that out. Okay, so I'm not going to look at all the systems Pat has looked at. I'm going to look at just one, and that is a silicon MOSFET. Okay, so what we found for the silicon MOSFET was that the semi-classical model is actually the one to use. Okay, so we are not we're not using quantum nuclear spins here, but these classical nuclear field vectors. Okay, so a lot of trial and error went into figuring that out. So here are results of the experiment in black and theory in red. And here's what we're getting out of the model. So we get out values for the hyperfine interactions. Now these are sort of mean field hyperfine interactions. Okay. We find it for the PB defect of 0.5 millitesla, and for the what we call just E for electron would be 0.15 millitesla. So it makes sense that this would be a larger one. Okay, this is the localized state, where this is a more delocalized state, so we expect a smaller hyperfine interaction. We get values for the Ks and Kd parameters. And you might ask, why do we use a semi-classical approximation? Does it have any validity? Well, we think it does. So, for instance, you have silicon-29. Yes, it only occurs at around 5% of the sites. However, it occurs as a nearest neighbor or next nearest neighbor at, of course, many more of the sites, up to, I think I want to say like 40 or 50% have a silicon-29 within a couple neighbors away. And some of these neighbors can actually have pretty significant hyperfine interactions. Okay, so they can play a role still for that defect spin. And moreover, there's also a lot of hydrogen in the system at this interface. And that we don't have as much of a statistical accounting of, but we know there's a lot there. So in addition to silicon-29, you also have a lot of hydrogen spins. So we do think that the defect spins are seeing, on average, a bath of nuclear spins. So let's home in on the small field effect there, which we can model quite well. here showing pretty good agreement of the effect, and I would like to say that these calculations are quite laborious. They take a long time, so fine-tuning these fits is very hard. So small adjustments of these parameters would yield better fits. And then looking at bias data, we can also find pretty good agreement with the experiment. Again, as I was saying, a lot of it's just simple computational time restrictions on trying to improve the agreement between data and theory here. So here's at various forward biases between 0.3 and 0.5 volts, and you know, as you increase this forward bias, you start seeing a much larger increase in this small field effect. And what's changing, as we find from the modeling, as you're increasing the bias, you're altering these kinetic rates, Ks and Kd. Why no resonances for the near zero field magnetoresistance? Okay, so for EDMR, we looked at the, where you had these level crossings, and you found there was resonances at them. Well, here we could plot, at small field now, we could plot the eigenvalues, and you see intersections like this right here. This is occurs at 3/4A, 3/4C hyperfine field. So you might think that there should be a resonance there. Well, there isn't, and our calculations show there isn't, but we can understand it, of course, more broadly. All right, so here's an example now. We have electron spin, here's the defect spin, here's the other spin, and here's the orientations, and we could have a flip-flop here, right? Magenta and black switch, in which case you get this, and now you have no bottleneck. You free up the spins for recombination. Okay, so that's a perfectly valid transition. Now the transition I'm showing you over here is not that transition, it's a different transition, it's this one. Here you have all spin down, all three spins, and hyperfine interaction can't get you out of the state, you're stuck here, okay? So you cannot transfer spin between the two systems to alleviate the bottleneck. So there's no possibility for a transition or resonance here, okay? So it's interesting, though, that this really depends on the spin of the nucleus, okay? So I'd like to talk now about some other features of the near zero field effect and make some predictions. So if we increase the spin of the nucleus more than one, we actually can get resonances in the near zero field effect. So here is an example calculation of 3 spin 1/2 nuclei. So I is effectively 3/2 here. And here's sort of the normal near zero field effect we get, but then we also develop these resonances out here. And here's the derivative data, and the resonances follow this equation here. So here it's 15/4 millitesla. So as far as I know, this has not been observed or attributed to any experiments thus far. Another feature is when you have also large differences in G factor of the two spins. So you have hyperfine and delta G resonances in conjunction. So this would happen at higher fields, and here's a calculation here of 2 spin 3/2 nuclei coupled to 1 electron spin. And you see these resonances out at much larger fields now. Again, these have not been observed, but hopefully we can find them. Okay, so that wraps it up. I've talked today about this NZ-FMR effect and how we can use it to study paramagnetic defects without using a resonator. Okay, I've looked primarily at this silicon MOSFET. It's a simple and cheap method because there is no resonator, and as Pat discusses in his talk, there's space applications for this. We've presented a model for the near zero field and EDMR using stochastic Little equations, and we're able to produce very good agreement with silicon MOSFET data. And lastly, I've put forward a couple neat effects of resonances when high spin nuclei or large delta G splittings are present. So I'd like to talk a little bit about future work, and that would be a more rigorous model of the silicon MOSFET, okay, by expanding the spin space considerably by looking at various numbers of the defects, or various numbers of the silicon-29 isotopes, okay, and basically doing calculations according to the statistical distribution of the silicon-29, and then also including the interfacial hydrogen, okay. So we're making progress along these lines by automating the fitting process, which would be very helpful because these will be pretty expensive calculations due to the large number of nuclear spins we'll have to be considering. And then looking for this quantum behavior in other systems will also be interesting. Silicon carbide is a promising candidate for that. It's also interesting because it has higher paramagnetic spin defect states, like 3/2 and 1. And there's also some ideas to use this as a magnetic field sensor. All right, so that's all I've got. Thanks for sticking around. I know I went over, but I didn't have a chair to stop me short, so I'll just leave my email on here, so please email me if you have any questions, and I look forward to hearing from you. Thank you.